Hey guys, so in this video we will be discussing on why should we perform a frequency analysis, and after that we will discuss what is a natural frequency and what is resonance, and once that is done, move on to discussing what is mode shape. After that we will talk about the different types of solvers that we have in SolidWorks frequency analysis, and after that we will perform a simple frequency analysis of a support bracket using SolidWorks simulation. And in the end, we'll just have a summary. So let's get started with our video. The first question that we will be asking ourselves is, why should we perform a frequency analysis? A frequency analysis is used to determine the vibration characteristics of a structure or component that is being designed or is already designed. So why is it important for us to know how an object vibrates or at what frequency it vibrates? To understand this, we need to have knowledge of two topics. The first one is natural frequency and the second one is resonance. You see, all physical structures have natural frequencies. These are frequencies at which the structure will tend to vibrate when subjected to certain external forces. These frequencies are dependent on the way mass and stiffness are distributed within the structure. Whereas resonance is a phenomenon in which a dynamic force drives a structure to vibrate at its natural frequency. When a structure is in resonance, a small force can produce a large vibration response. So what does this mean in practice? When a force is applied to a physical object, it vibrates. When a force is applied at the object's natural frequency, it goes into resonance. And at resonance, the amplitude of vibration is at its highest. For a better understanding, let's take a guitar. When the different strings of the guitar are plucked, different sounds are produced. The type of sound also varies when the location at which the guitar is plugged varies. Similarly, all physical objects have multiple natural frequencies and can resonate under the right conditions. Sometimes the natural frequencies are excited by external forces acting on the object, which creates vibration. These vibrations may be so small that the human eye cannot see them. Sometimes these vibrations are desired and sometimes these vibrations are not. A good example for desired vibrations is the guitar, just as I explained. And the main reason behind us performing a vibrational analysis is to prevent or minimize the undesired vibration in a system. A good example where this is undesired and destructive is in the case of a wine glass. Wine glasses have a certain natural frequency in which they vibrate. So when we direct sound waves at those exact frequencies, resonance occurs, and this causes the wine glass to vibrate rapidly. And after some time, it just breaks. Another great example of resonance being destructive is the Mexico City earthquake, which occurred in 1985. During the earthquake, all buildings which had up to 6 to 15 floors were absolutely destroyed to rubble, whereas the rest of the buildings had a relatively minimal damage. After investigation, it was found that the frequency of the earthquake matched with the resonant frequency of the building, which had 6 to 15 floors. The next topic we will be talking about is the mode shape during vibration. A mode shape is the deformation that the component would show when vibrating at the natural frequency. The resonance frequency of the vibrating object will vary with different mode shapes. There are three different types of solvers which are used to perform frequency analysis. They are the direct sparse solver, the FFE plus, and the Intel direct sparse solver. Based on our simulation, we can either select them manually or click on the automatic solver selection checkbox to automatically choose them. How they work and the specifics behind the working of each of these solvers is beyond the scope of this video. What I'll do is give you a brief explanation as to where these solvers are used. The automatic solver selection is the default option which is given to almost all types of simulation modules, be it static, buckling, thermal, or frequency. But should you decide to manually select each of these solvers, you can just click on this drop-down box and select either one of them. In case of a multi-area contact problem, where the area of contact is found through several contact iterations, then the direct sparse solver is preferred. While all solvers are actually efficient for small problems, there can be a big difference in performance in solving large problems. In general, the FFE Plus is actually faster in solving problems with degrees of freedom over 100,000. It becomes more efficient as the program gets larger. The direct sparse solver requires about 10 times more RAM than the FFE Plus solver. It becomes faster with more memory available on your computer. This solver leverages multi-core processing capability and improves the solution speed for static and nonlinear studies. When the moduli of elasticity of the materials used in the model are very different, let's say in the same model you have two different materials like for example steel and nylon, then iterative methods could be less accurate than direct methods. In such scenarios, direct solvers are recommended. When performing analysis where there are no interpenetration contacts and bonded contacts, direct solvers tend to solve these much faster. So with this, let's move on to the software part. So let's start off by running a simple analysis of these three brackets. The main objective of our simulation is to determine which of these three brackets are most resistant to vibration. So here we have a normal bracket and then a thicker, it is a little bit more thicker in dimension, and then we have a normal bracket which has a stiffener. So what we will be doing is we will be performing frequency analysis on all three of these components individually and along with their assemblies, and we will be finding which of these three have the highest amount of resonant frequencies. So let's move to the software. So here is our stiffener. I've opened this up in SolidWorks simulation. To perform a frequency analysis, we just need to first go to new study and press on the frequency option here. I'll just name it to frequency normal and press on OK. I've already given the material for this as cast alloy, the modeling tab itself, so no need to give any material right now. So our next course of action would be to give it fixtures. So right click on it and give fixed geometry. And we will be fixing these 4 holes. So I'll just do the same. Again, please always make sure that you select the cylinders, not the circle, because just a small mistake can give you varied results. So I'll just go ahead and press it, Ctrl 7 and press OK. So we fixed the geometry here. So the next one is external loading. Here the external loading is actually not the source of vibration. So this is one confusion most people have. Here the external load is just a static preloading which already exists in our component. So for example, let's say we already have a load of 100 Newton which is already existing on this bracket. So we want to find the resonance frequency of this bracket while we have the load on it. Only in that case we will be giving in the external load for this bracket. Right now we just want to find the resonance frequency of this bracket without any external loading. So we're not going to add any values to it. So our next task at hand would be to mesh it. So right click on the mesh and click on create mesh. Here let's go to mesh parameters and curvature based mesh. Here we'll set it as 4 millimeters. Now press on OK. And let's wait for the model to be meshed. Okay, our model has been meshed. Alright. Now let's run this study. So the simulation is done. Here we can see that we have 5 different options. So each one of these are different mode shapes, and we also have the respective resonance values for them. So the first one is the mode shape. Here you can notice that this part of the bracket will move up and down. We can actually animate this. So right click on it and press on animate. So let's just wait till it generates the frames. So you can see that this part of our bracket is moving up and down. Similarly, let's click on the second mode shape. So here you can see that this part is actually moving in opposite directions. So while this one is going down, this one is actually going up. Let's animate that. As I said, here's the animation. Let's press OK. So these are the different mode shapes of our bracket. And each of these mode shapes will have a different resonance frequency. We can actually check the resonance frequency by going into results, right click on the results, and here click on list resonant frequencies. Here you can see that we have the resonance value in radians per second, hertz and seconds. So the resonance frequency of the first mode for this bracket is around 1755 hertz. So we'll just note that down. So we'll just remember that one. And let's go ahead and press close. We can also define how many modes we want in our simulation. So to do that, we need to go to the title here and right click on this and select the properties option. So as you can see that by default, we have the number of frequencies radio button checked here. And by default, we have the number 5 here. So the default is to calculate the lowest 5 frequencies which will occur to the bracket. So should you want to change the number, you can just press on these arrow marks to either increase or decrease, or you can just go ahead and change your number. So let's say you want to find 10, you just type 10. So by default, it is always 5. So the next option that we have is the calculate frequencies closest to. So let's go ahead and click on the checkbox. So what this option does is that it calculates a n number of frequencies which are closest to the specified value. So let's say we are entering our input value as 2000 Hertz and the number which is input here is 5. So here we have given the value as 2000 Hertz. So what it does is it will calculate 5 frequencies which are closest to 2000 Hertz. So for example, let's give the value here as 6000 Hertz and let's run the simulation again. As I've changed it, I'll just press run study. Okay, so we have our result here. So let's go to results, right click and list resonance frequencies. So here you can see that all of these values are somewhat closer to the 6000 we inputted here. Initially our first modal frequency was around 1700. Value which is given here was the resonant frequency of either the third or the fourth mode, and here you can see that it has changed entirely. So that's the function of that option. Now let's press on close and move on to the next option we have. And the next option is the incompatible bonding options. This option is used to define the type of bonding. So by default we'll have the automatic option selected here unless you manually change it. So what does this option do? By default, the type of bonding which is given is surface to surface bonding. So during a simulation occurs, if the surface to surface bonding contact slows down our solution considerably, then what the solver does is it automatically switches to node to surface bonding. The next one is the simplified bonding option. This option is used to override the default surface based bonding and resume to node based bonding. We need to use this option only in case we run into performance issues when solving models with extensive contact surfaces. The next option is the more accurate option. So what this option does is that it applies the default surface based bonding contact. This results in a longer solution time than the node based contact formation, but it also gives us a much more accurate solution. So to summarize what all three of these do, the automatic option is used to automatically switch between either surface based to node based or node based to surface based on our solver. The simplified option is used to exclusively select the node based bonding, and the more accurate option is used to exclusively select the surface based bonding. After that we have the solver options. Here, as we just discussed, this option is used. This is where we select the type of solver. I've already discussed on what direct sparse solver is, FFE Plus and Intel direct sparse. So I'll not be talking much detail about that one. A frequency simulation of our normal bracket will now do the same for the thick bracket. I'll just go ahead and minimize this one. And let me open the thick bracket. Right off the bat, you will be able to notice that the thickness of this bracket is much higher than the normal one. So we'll just do the usual. Let's go to simulation. I've already activated the license here. Go to new study. And under new study, you press frequency. I'll name it thick bracket, and I'll press OK. Control 7. Since I've already given the same material to this one, we'll just not define anything. Let's go to fixtures, fixed geometry. So what I'm doing right now is just the same that I did for the normal bracket also. So I'll just be fast forwarding it right now in the clip. Once I get the results, I'll just show it to you. Okay, so here we have our result here. So as discussed, let's go ahead and look at the resonant frequencies. Right off the bat, you can notice that the resonance frequency of this thick bracket has actually increased. So for the normal bracket, the resonance frequency of the first mode was around 1700. And for the thick bracket, the resonant frequency of the first mode is 2480. So the main reason why I am specifically mentioning the first mode is because by default, what the solver does is it gives you the lowest 5 frequency values. So that's why I'm considering mode 1 as our benchmark for comparison. So you can notice here that it is 2480. It is about 724 Hertz, much more than that one. So let's just note down this value, and now we'll go ahead and do the frequency analysis of the bracket which has a stiffener. So I'll just close this one and minimize this. I'll go to the bracket with stiffener. So it is this one. Let me just maximize this one. Here you can see that we are right now in the model option. Here you can see that I've added a small stiffener in the bottom just to increase the stiffness of the bracket. So I'll just press Ctrl 7. Let's go to new study. So right on, from here on, it's going to be the same again. So I'll just be fast forwarding the video. Okay, so we have our result here. Here you can see that the mode shape is somewhat similar in all 3 of the brackets. Even in the normal bracket, this horizontal metal piece was actually moving up and down, and in the thick bracket it was moving up and down. The same way here, even for this bracket with stiffener, it is actually moving up and down. So let's go and check the results here. Let's press on the list resonant frequencies option. So here you can see that the frequency value for the first mode shape is around 2486, and for the thick bracket the mode value which we received was 2480. So here you can notice that not only have we increased the resonance frequency of this bracket, but we have also saved a lot of weight. I'll prove that in the end, because I've also done a small mass comparison for all 3 brackets. So just remember, right now the bracket stiffener has the highest amount of resonance frequency. So it is 2486. Let's go ahead and close it. So now that we've actually done a frequency analysis for all 3 brackets, let's go ahead and do the same frequency analysis for the assembly also. So I'll just minimize this one and open the assembly. So the first assembly that I will be opening, that of the normal bracket. So I'll just minimize this. So this is our assembly. Here you can notice that we have 2 brackets over here and here, which are actually holding the entire assembly up. This is just a plain model which I made. So the main purpose of these two brackets is to hold this one. There will be more structure here. Just for the sake of simplicity, I've not added it here. So let's go ahead and run the simulation. Here, let's go to parts. And I've already given the material for these two as cast alloy steel. So for the base, this part, for this one also we'll mention it as cast alloy steel. So let's go to apply favorite material and select cast alloy steel. The next job of ours will be to fix the geometry. Again, this is all much similar to what I've already done. Let's press the select the holes. I'll just select all of them, because in these holes is where the entire geometry will be resting upon. So let's press OK. The next job would be to mesh it. So let's just create a mesh, curvature based. Let's go to mesh parameters, curvature based, and we'll make it a 15 millimeter mesh. So what this means that the maximum size of our mesh element would be 15, and the rest of the parameters are just taken in automatically. We can also change these ones if we want to. And the minimum element size would be 3. Let's press OK and let the solver mesh it. So we have received our meshed model. The only thing that is left is for us to run the study. I've already run the study myself in the background. This takes a little bit of time for me, so I'm just not showing it on screen. So let's just press on frequency 1 to look at our results. Again, just remember I've used the same options here. I didn't change anything. The mesh was the same one. I used a 15 millimeter mesh, and here also we've used the cast alloy steel, and the fixtures are also much more similar. I mean, are the same actually, not similar. So let's press the first one. So here you can see that the first mode shape would be up and down. So the entire structure will be moving up and down. It is also much similar to the mode shape that we received for the individual bracket. That means this horizontal piece will be moving up and down. So let's check the resonant frequency of this one. Go to options, right click, go to list resonance frequencies. Here you can see that it is 234.79. That is the lowest resonance frequency for this one. We'll keep this one as the benchmark for the rest of the brackets too. I'll press close. I'll just minimize this one and move to the next. So this is with stiffener. So I'll just maximize this one. Again, I've already run the simulation for this one with the same parameters. I've not changed anything. So let's select the first amplitude. Again, it's the same. It's moving up and down. Here you can see similar mode shape, similar to the one which we saw in the individual frequency analysis. So I'll just press Ctrl 7. Let's go to results and list resonant frequencies. Here you can notice that it is 276.87. This is much higher than the resonant frequency without the stiffener. Again, let me note down this one and press close. I'll move to the thick one, and this is the thick model. Here again, these are the thick brackets. I've also run the simulation for this one. Ctrl 7, the first amplitude. Again, it's the same. It's moving up and down. There are the other amplitude also. The only reason why I'm not comparing those ones is because our benchmark right now, which is the first amplitude. So press on results and let's list the resonant frequencies. So here you can see that it is 298. It is actually much higher than the 276 of the bracket one. So let's just note this one now and press close. Ctrl 7. So now that we have all the required data, let's now compare all the resonant frequencies for all the brackets. So let me just jump into the PPT. Okay, so here is our PPT. We have our normal bracket, thick bracket, and also the bracket with stiffener. The values that we obtained are, for the assembly model, the normal bracket had a resonance frequency of 234 Hz. This is not the resonance frequency of just the bracket. This is the resonance frequency of the entire assembly. For the thick bracket, it was 298 Hz, and for the bracket which had a stiffener, it is 276 Hz. The same way, we also performed an individual analysis. So for this one, it is 1756 Hz for the normal bracket. For the thick bracket, the individual resonance frequency was 2480, and for the bracket with the stiffener, it was 2486 Hz. So I also checked the mass of each of these brackets. You can actually do that directly in the SolidWorks. Before ending this PPT, I'll just show it to you, don't worry. So the mass of the bracket for this one is 1461 grams, that is 1.4 kgs. For this one, it is 2.191 kgs, and for this one, it is 1534 grams. So here you can notice that the increment is much higher, and here it is very less. So with a much higher increment in mass, we have reasonable increment in the resonance frequency values. Here, with very little increment in mass, we have a much appreciable increment in the resonance frequency. So this is the major application of frequency analysis. This is actually used to compare different resonance frequency of different structures to determine whether they are safe or whether they are not safe. So I'll just go to the SolidWorks window and show you how to calculate the mass of this bracket. Okay, so I've opened SolidWorks, and here is our bracket. This is the normal bracket, not the thick one, not the one with the stiffener. So how you find the mass is you just go to Tools, Evaluate, Mass Properties. Here in this dialog box, you'll have pretty much all the information that is required. Here you can see the mass value. It is 1461 grams. So how the software calculates is once we define a material to it, the software will have a database of the density of the material, and based on the geometry, it will calculate the volume. So mass is just volume into density, and we get our mass here. And we also have our volume, the surface area, center of mass, all the data here. And for now, the only thing that we require is the mass. So that's here. And let's just close it. Okay, so let me just jump back into our PPT. Let's move on to the summary part. So in the beginning of this video, we first talked about what natural frequency is and what resonance is. After that, we had a brief discussion on the different examples of resonance. And after that, we had a discussion about mode shapes of vibration. Once we were done with that, we performed a frequency analysis for a bracket. And then in the end, we compiled the results and had a brief discussion on the resonance frequencies of each of those brackets. For your challenge, we have something which is interesting. Let's go to the SolidWorks assembly. So here I have the bracket assembly. This is just a normal bracket without increased thickness or stiffener. So let's just go to the frequency analysis. Here in the beginning of this simulation, I've told you the main function of the external loads was to take the static preloading into consideration. So what does static preloading mean? So here you can see how the brackets function. They're just used to support this base on, say, a wall or a cantilever or whatever. So these are just brackets which are used to support something. Here I did not give any values of external load while running a simulation of the bracket. Let me just open the individual brackets. So here we have our bracket. So while we actually ran the frequency analysis, we gave our external loads as 0. But for your challenge, what it will be is we will provide you all model of the thick bracket, the model of the normal bracket, and the model of the stiffener bracket. You will have to find the mass of the loading object. We will either give it to you as a model or it will be mentioned in the question. And then with the help of that, you will be performing an external load. And then you will be creating a proper report of your findings with step-by-step data for everything. Well, that's it for this video, guys. This is the last video of our course. So this is where we part ways. Hope you've enjoyed our content and most importantly learned something. If you do feel that you've learned something, do recommend our courses to your friend circle.